G'day folks, Michael from Geology Noob bringing you a quick overview of the tectonic evolution of the Western United States from 40 million years until the present day. So most of the work here is a summary of other people's papers and previous work, and I've attempted to bring it together quickly in a very short presentation. So during the show, I'm going to talk about the cessation of shallow subduction in the San Juan volcanism, the formation of the Juan de Fuca and Cocos plate, the formation of the San Andreas fault, and the opening of the Gulf of California. There is no doubt that I will forget many things and get many things wrong. I do apologize, but hopefully I'm roughly on the right track. So from 40 to 30 million years ago, the East Pacific rise and the Farallon plate was continuing to move to the northeast and subduct beneath the North American plate. And the subduction zone of present-day California is similar to what we see in the Andes today, which is a shallow subduction of a hot new slab. This new hot slab, because of its buoyancy, was basically thrust up against the underside of the North American plate and the lithosphere, and it floated and was carried all the way as far inland as Colorado. And it wasn't until it reached Colorado that it finally cooled and started to dip away. So the cooling of the plate and the dipping or the removal of it from the base of the lithosphere created what was called the San Juan volcanism. So this was a period, roughly 35 to 30 million years ago. And essentially what happened is, as the shallow subducting slab went further inland, it took with it a lot of volatiles. And when I say volatiles, I'm meaning water, and allowed the formation of a lot of hydrous minerals along the base of the lithosphere. So it essentially fertilized the lithosphere. Once it reached a temperature where it was cold enough and dense enough to either dip away or break away, snap off, and then sink into the mantle, into the asthenosphere. The asthenosphere, which is a hotter ductile material, flowed upward, contacted that fertile lithosphere, and then because of the addition of volatiles, reacted, causing melting and large-scale volcanism. I believe I read, and please don't quote me, somewhere that they know during this period there are at least 10 singular eruptions, and each eruption was 10 times that of the Mount Helens eruption. So that's some pretty epic volcanism, to say the least. So then we go into, and I just want to say as well that it was that onset of volcanism across the entire area which is the real evidence and the key to say this is the time when the slab detached or the slab broke off. From 30 to 20 million years, the Farallon spreading center, so the Farallon plate is the plate that's subducting under North America. The spreading center between the Pacific and the Farallon subducted between the North American plate, beneath the North American plate, and this resulted in the formation of the Juan de Fuca and the Southern Cocos plate. And it was also the very beginning of the San Andreas fault as well, and I'll go in a little bit more detail on the next slide. So, evolution of the San Andreas fault. If you look at the cartoon on the left, you'll see up the top we start at 30 million years, and you can see the red lines are the spreading centers or the mid-ocean ridges, with the Pacific plate spreading on the one side and the Farallon plate spreading on the other side, and the Farallon plate is being subducted beneath the North American plate, and you can see how close the spreading centers are to the subduction zone. This means that the plate that's being subducted is hot, and so it's not very dense, and so it's buoyant, and you have the shallow subduction like I've previously spoken about. Once you get down to 20 million years, you can see that a part of the ridge, of the mid-ocean ridge or the spreading center, has now subducted beneath the North American plate. And this forms two triple junctions. So you can see the first triple junction in the north is labeled M, and the other one in the south is R. They have names that go with them. The north one's called the Mendicino. Look, I'm Australian, my pronunciation is terrible, so I'm just going to call it the M triple junction. And these are really, really important because the north is these are both subducted mid-ocean ridges. So here you have hot material being brought up from the mantle and being applied beneath the North American plate, and then as the plates continue to subduct, this upwelling of heat continues north and south along the same path of the subducting mid-ocean ridge. So this is sort of like unzipping. I like to think it's like having two blowtorches and having them underneath the North American plate, and you're just running them north and south away from each other. And essentially what's happening now is that you're causing a transform fault because you have a collision of the plate hitting of the Farallon plate and the Pacific plate hitting the North American plate, and then you have these two hotspots underneath it that are moving north and south and separating that part of North America. So you end up getting a fusion where essentially a part of the North American plate joins with the Pacific plate, and then on either side of it you have the continued subduction of the Juan de Fuca and the Cocos plate. Now the Farallon plate becomes the Juan de Fuca and the Cocos plate because essentially the middle bit of plate that was joining them together that made it overall the Farallon plate has been subducted now. So you just have these two individual plates that are separated by the Pacific plate. So if you ever see, something that says that the Farallon plate became the Juan de Fuca and the Cocos, it's just because the mid-ocean ridge that was in the middle of them, the part of the plate that was in the middle of them, subducted, and that's why they formed. So that's where you get the, and then as you progress, you get to the San Andreas Fault as we know it today. You have the Pacific plate, which is headed roughly in a northward, northwest direction, and then you have the North American plate, which is heading relatively south, and then you have this collisional force, and then you have them both moving in opposite directions and grinding away from each other, and then added in there you've got subduction to the north and the south of it. So quite dynamic forces, but it's this movement, collision and subduction which cause the San Andreas Fault to form. And there's also evidence of the migrating triple junction heading north along the spreading center. This is a series of volcanics that young as they head north, so they're older in the south, and then as they go north they're younger and younger. And just some evidence of that northward movement of the western side, on the western side of the San Andreas Fault. When you match up different lithologies, so different types of rocks and different sedimentary deposits and so forth on each side of the boundary, they don't line up anymore. It's very clear that that there's been this northward movement, and I think today it's up to 470 odd kilometers that the land has moved to the north on the westward side of the San Andreas Fault. 15 million years, the east spreading center becomes the San Andreas Fault as we know it today, and the Gulf of California begins to form as the Pacific plate grinds northward and extends parts of the North American plate. So if you go to the south, towards South America, you have the Pacific Rise, what's called the Pacific Rise, and essentially that's the spreading center that is responsible for the shallow subduction beneath South America. So that's where the new plate material is being created, and it's that's being subducted. Now the very northern tip of that Pacific Rise subducted underneath the very bottom of North America, and it's the subduction of that spreading center which has caused the Gulf of California to open. So you have this again, very much like the San Andreas Fault, where you have the spreading center of the Farallon Plate and the Pacific Plate subducting. Here you've got the Pacific Plate again, the spreading center from the Pacific Plate subducting, and then because the land along that stretch of Baja California it's all old accreted terrain, so it was all volcanic island arcs and this sort of stuff that was accreted over time as the plate subducted. It was already really quite weak. So once this mid-ocean ridge went under, hot material came up, convection, it causes extension, and that area rifted really quite quickly. And then when we get to present day today, so like I said, guys, don't quote me because these are approximations and ballpark figures, but there's about 4.5 centimeters per year of movement in opposite directions between the North American plate and the Pacific plate. And then you have about 2.5 centimeters of that, so probably about half, a little bit more, is accounted for in movement in the San Andreas Fault. But there's another 2 centimeters which you can't find where that movement is going, and it's all a force. It all has to go somewhere. So there are a lot of faults all through this area which are probably accounting for a lot of it, but there's also that accumulation of stress, which is why you do have the earthquakes in the period. And it's really quite a dynamic area, because in the very south you have an extension area and a rift, then you go up to a transform boundary at the San Andreas Fault, and then to the north you have a subduction zone. So that's it, guys. If anyone's got a high school report or something they need to do on the formation of the San Andreas Fault, you can use this, and hopefully you found some value in it. Thanks a lot, and I'll see you in the next video.